signal processing. You had the final tutorial this morning, and these 2 last hours this afternoon I'm going to be using for revision to go through some of the past questions that we've got. So in fact all of these questions, the questions and the solutions are already available on there. Yeah, please turn devices on to silent, please, during the lecture. And so I'm going to go through the sort of topics that might come up in the exams. So I'll be covering one question on linear time invariant systems, a question on Z transforms and pole zero diagrams and stability, question on discrete Fourier transform, fast Fourier transform, convolution, a question on FIR filters, one on IIR filters, and one on multi-rate signal processing. So some of the techniques from here, the solutions that I'll go through here, I'll really be giving some pointers to the sorts of things to think of. From here, the revision plan is already available on Surrey Learn, and all the questions and example solutions are on Surrey Learn. Sometimes you might find the example solutions with the exam papers are a bit brief, rather than going through a long explanation, because they're really focused on guidance for the marker or guidance for an attempt, just to see if you've got the right idea, rather than necessarily an explanation of everything. But most of the topics that come up will also have some corresponding question related to that in the tutorial material, so you'll probably see a longer version of that. But within the last part of many questions, there's perhaps a slightly challenging part or a slightly different part, so those things might not be exactly the same as has come up in tutorial questions. So what I'm going to propose to do is to go through the first of these 3 questions in sort of 45 minutes left in this lecture, and then I'll go through the next 3 questions in the remaining lecture. So I'll try and take questions as we go through here. So I'll sort of talk through the questions using the solutions that we've got, rather than draw them out by hand. But if there are things that you'd like me to expand on, then let me know, and I'll see what I can do from there. And then just finally a note, as I mentioned before, that for this year it's an all 3 questions exam paper. So be ready to answer anything on this or related topics in there, because any of them might come up. Okay, so let's pick up the first one of these. So this was 2017-18 question 1 on linear time invariant systems. So I'm going to zoom in on this so that we can see the question and see what we've got from here. So as is common with other types of exam papers, here we have a multi-part question with percentages down the side, and that should give you a rough idea of how much is covered within the question. And also to give you an idea, each question is 100 marks in terms of its percentages. So altogether we've got 300 marks across the 2 hours of the question. So if my mental arithmetic is sort of any good, that's about 4 minutes for 10 marks, something like that. So there's not a huge amount of time to go through that. If we could, but I should probably get a calculator out to calculate that. So 2 hours, so we have got 2 hours, that's 120 minutes. Divided by, if we divide that by 30, yeah, 4 minutes is about 10 marks. So if you've got something that's 15 marks, then that's about 6 minutes for that part of the question. So that should be a guide to you for how much time to spend on that. So sometimes you'll find some bookwork parts at the beginning of a question. If it's a 10-mark question, that says spend about 4 minutes, maybe 5 maximum on that. don't write 2 pages of something that's going to take you half an hour to do that, because you'll run out of time for the exam. Okay, so let's just have a look at this question overall to see where it's going, and then we'll come back to look at some of the details of the solutions for this. So define the Kronecker delta function d of n. Using this definition, show that the values of xn of any sequence can be expressed using this formula. Okay, so the delta of n formula. Anyone want to give me a suggestion for the definition for the Kronecker delta? What does the Kronecker delta do? Yes. Yeah, exactly. So that's in fact what we've got for, if we look at the solution now, for that, which is in the solution part. This is an example of the definition for that. It's actually slightly easier than we might want for the Dirac delta function, but this is available in the solution. And then the second part of the question that we want to show is this, the second part here, that we can show that x of n is sum from k equals minus infinity to plus infinity delta of n minus k x of k. So this is a filtering property. It says if we take an inner product of x of k with delta of n minus k, then it will pull out the value where n is equal to k, and we just need to show that. And so this is the sum that we've got here, the sum delta of k, x of k, but because of this property that we've got here, all of the values in the sum are 0 except where the thing inside the bracket is equal to 0. So in other words, it's this value where n is equal to k. So that's exactly x of n. So that was fairly straightforward for that one, and so actually that's about 6 minutes worth, and so as long as you know roughly where you're going, that should be okay. Any questions on this bit? So this is a reasonably straightforward bit to start. Okay, all of these are available in the solutions, so you can get them from sorry. Okay, now let's take the next bit. So a linear time invariant system must satisfy the scaling property and the sum property of linear systems plus a time invariance property. So define the meaning of these 3 properties. So this is a bookwork part of the question. This is just remember what these properties are. So what's the scaling, the sum property and time invariance? Anyone want to give me a suggestion of the sum property? The linear time invariant system. Yes. Yes. So if we pick out the sum property here, let's use this one. This one here. If we've got a system F, or in this case in my diagram system H of x plus y is h of x plus h of y. That's really what the sum property is for a system. And you could also draw it in a flow diagram. The question doesn't ask you for a flow diagram, but that's an alternative way that you could give the explanation if you want. We've only got 5 marks for this part of the question, in that there's, for the whole thing, there's, if I scroll back down here, we've got 15 marks for the whole thing. So you're not expected to write up a long thing. Again, you've got about 6 minutes for this. So that's 2 minutes for each bit. So a brief answer is enough. Here's the scaling property that h of some alpha plus x of n is alpha times h of x of n. So again, you can do it with flow diagrams if you want, but don't spend too much time on that so that you've got enough time to do the rest of the sequence, do the rest of the paper. And time shift invariant, so roughly what is time shift invariance about? Yeah. So time shift invariance means that you can shift. If you shift the input, then the output will shift by the same amount. So that's what it means by time shift invariant. And again, you can either put it as a formula or in words or as a diagram, so whichever you prefer. So that's a bookwork part, and normally we'd expect an exam paper to include some bookwork, some problem solving, and a sort of challenging bit at the end. It depends from question to question, but maybe 20-25% bookwork, maybe 50% working out, and maybe a sort of 25% challenge. But again, they'll vary a little bit between each question. And the idea for that is that even if you can't solve any questions, but can at least do some bookwork and remember some formula, you might get enough to be able to pass. But in order to get a really good mark, a really top mark, then you need to do the challenging bit at the end. So let's have a look at now the next parts in this question. So we've done part B, now we're on to part C. So suppose that a system H is given an input sequence and x of n and produces an output sequence y of n. In each of the following cases, determine whether or not H is an LTI system, so LTI linear time invariant. We just had defined in the previous question. So here, so the first one, y of n is equal to 1. Anyone want to guess whether that's a linear time invariant system or not? It's not, okay. Somebody else want to suggest why it's not?
That's how much you're allowing people not to be.
So these two together cannot be multiplied.
So how about what property might it? Yes. That's right. It's not linear, and so let's have a look at that from the from this example here. That it's not linear because, for example, it won't satisfy the scaling property. So what's supposed to happen with the scaling property is that you multiply the input by alpha, the output should get multiplied by alpha. But the output here is constant no matter what the input is. So we multiply the input by alpha and the output doesn't change. So it fails to satisfy the scaling property, therefore it's not linear. Yes? So we have, if I go back to the question here for just a second, we have that y of n is h of x of n, so there is an input, but the input is being ignored. So we can multiply the input by something and it doesn't do anything. So the output is just a constant one no matter what the input value is. So it's a bit of a trivial system in this sense, but you can still get this. And what this says is that it's not a linear system because it fails that property. It would also fail the summation property as well, but this is the easiest one to show. So the second one, y of n is equal to x of 2n. What do we think about that one? It's not linear. Okay, anyone want to suggest why it's not linear? Oh, sorry, why it's not linear time invariant? Yeah, so for this one, the shifting doesn't work. It might be easier to show that one with a diagram, but if we look at this example here, so we've got y of n is x of 2n. If we were to shift our x by some k to make it a sort of x1, then the output y1 is x1 of 2n, so we've got a different x1 value. But if we expand that, substituting in the n, x is now 2n minus k, but that's x of 2 times n minus k over 2. So that's y of n minus k over 2. We substitute that. So there are various ways that you can show this. You can also do it by diagram, just to say, look, we're taking every other point, and if we shift our input by, say, if we shift our output by 1, we've got to shift the input by 2 to make the same shift. So there are lots of ways of showing it, but this is not time shift invariant. So this is an example of a sample rate change. So this is actually, in this case, a decimation operation. So it only takes every other operation here and it throws away half of the operations. So this one is not linear time invariant. So the final one that we've got in here is the case for y of n is x of 2n plus x of n minus 1. This one's fairly straightforward. This is the sort of thing that we would expect to find as a type of filter. What type of filter would we call this? Yeah, it's an FII, it's a finite impulse response filter, because it only depends on x of n and x of n minus 1. There are no funny multiples of n in there to make it a sample rate change. There are no constants, and so in that case it will be linear and time invariant. And actually, if we look at the marks that we've got for the question, we've got 20% here, so we're going to perhaps need to spend a little bit more time working through the different cases of this one. So let's have a look at the cases here. So first of all, we can look at the scaling properties. So scaling property, we need to check that if we replace x of n by alpha x of n, we should get the output changing to be alpha y of n. So let's do this. We put 2 alpha x of n plus alpha x of n minus 1, which is the stage. We can just take the alpha out to give us alpha of 2x of n plus x of n minus 1, which sure enough this is actually y of n. We can just substitute the y of n back. So we've demonstrated the scaling property. Then the next stage, the sum property. So for the sum property, if we've got two sequences, y1 and y2 of n, where each one is an x1 of n plus x1 of n minus 1, the y2 is 2 x2 of n plus x2 of n minus 1. So in other words, we've got two slightly different sequences with slightly different inputs. If we had an input x1, which was the sum of those two inputs, then the output should be the sum of these two outputs. So we can just run this and see if we do it. Our x of n is 2 of this x of n, which is this sum x1 of n plus x2 of n, plus x of n minus 1, which is the sum x1 of n minus 1 plus x2 of n minus 1. And so just by rearranging the terms here, we can pull the x1 terms together here, the x2 terms together here, and then show that it separates into this term. So this means that we've now demonstrated, because of the sum property and the scaling property, that this is a linear system. So the remaining thing is just to show that it's a time invariant system. So for time invariant, let's take x of n and replace it by x of n minus k. We've shifted our input by some k. That means that the output y of n becomes 2x of n minus k, substituting in here, plus x of n minus k minus 1. So we've got n minus 1's become n minus k minus 1 here. sure enough, x of n minus k plus x of n minus k minus 1, which is exactly the x of n. So we've shown that the time shift invariant property works as well. So since all of those three properties, sub-property, scaling property, and time shift invariant, this is linear time invariant system. Okay? Right, so that's that part. And so that's really the main part of the question so far for us here. Then the last part is perhaps the more challenging part of this question, part D. So this one is really pushing to see how familiar you are with this material. So suppose that H is a linear time invariant system, as we talked about it before. Using the properties of scaling, sum, and time invariance show that the system output sequence can be calculated by this convolution. So where H of n is the impulse response. So this is something that we actually did do in one of the tutorial questions. So a couple of the tutorial questions led us through to this sequence. But I'll just go through this one anyway, just to illustrate how this is, because it's actually fairly straightforward to do this, but you really need to be familiar with the material to know how to get on to each step. So here's the part of the question from here in the solution. So we really want to show the convolution formula. So first of all, we know that the system is linear time invariant. Because of that, we've got those three properties that we just had before. We've got the sum property, we've got the scaling property, and we know that this system here, y of n, which is x of n, we know something about x of n, because if we look right at the top of the question, there's actually a hint to how we can deal with this. This very first part A, we're going to use this, and this is used in the tutorial. X of n, we're going to break this into a delta n minus k, x of k. So, although it's not specifically hinted in the question, this is why this is an advanced piece of the question. If you can spot that we can do something useful with that, that can get you started on this part of the question. And where this is going to be useful is that this delta of n minus k, by the time we operate the h onto delta of n minus k, we're going to get the impulse response for the system. So what we showed in part A allows us to replace h of x of n with h of this sum, x of k delta of n minus k, summed from k equals minus infinity to plus infinity. That's a key part for this question. If you didn't know that this was a useful thing here, that would be quite difficult to progress. But for this one, it's because we need to get this delta of n minus k so that there's an impulse response in there somewhere. So from the sum property, we know that h of a sum of things is equal to the sum of h of things. So it allows us to change the order of summation and the system operation. That gets us to this stage. So we've got the sum out here. Then the scaling property. Inside this sum, x of k is not a sequence over n. Within each one of these k from minus infinity to plus infinity things, h of x of k is just a constant inside that particular sum term. So that means that we can take that outside of the h. So we've then got the sum over x of k, h of delta of n minus k. This is going to be where we get to use our time shift invariant property from. And because h of n is simply the impulse response of the system. So in other words, you put an impulse delta of n into the system, you get h of n, little h of n. That's our impulse response. Now we use the time shift invariance property to say that h of delta of n minus k, if we shift the impulse by k, the output will also shift by k. So that's that final step. So that means that we can replace this h of delta of n minus k by h of n minus k. And that's it. So you can see from here that we have used the sum property, the scaling property, and time invariance to get this. And this is really gives us this convolution operator. We haven't done anything about the commutativity of the covariance operator, but it has given us what we wanted. So this is quite a challenging part for this question, but you can see that there was another part of the question that was trying to help you in that, but it wasn't specifically telling you the steps to do. Right, so that's really question one. So we can see from here 30% on this question. That's about 12 minutes for that part of the question. So even if you couldn't remember all of this part, if you can remember what the time shift invariance property is, if you can at least state how the sum property might be used, if you might remember parts of this, at least write something, because there might be some marks that you could get for even a partial solution for this part. And so that will help to award something. As usual with these, because the marks are awarded by section as they're laid out here, if you don't write anything for a section, you're not going to get any marks for that section. So just please write something, and then that will help the examiner to give you, at least have a chance of giving you some marks for that part. Right. Any questions on that part, or I'll go on to the next question? Okay. Good. So, as I said, all of these are available on Surrey Learn as solutions, so you can see. Go through those a little later if you want to. Okay, so this is from the 2016-17 exam. This is question 1, and is really about Z transforms and inverse Z transforms and pole zero diagrams, that sort of thing. So let's have a look at the question here. So here we've got a question that gives us a causal linear time invariant system with the following transfer function. So we're told that it's a causal system. This should help us with something later on. So if we think about stability, what do we know about the stability of a causal system? How can we tell, thinking about zero pole diagrams and so on, how are we going to use causality to say when is a causal system stable? Yes, the poles are inside the unit circle. So this is the sort of thing that is going to help us by, if we didn't know it was a causal system, we wouldn't be able to use that property of just looking for the poles inside the unit circle. So that's just looking a little bit ahead for where the question is going to take us. Here we've got something 1 over 1 minus something z to the minus 2. We want to derive a linear difference equation relating the output y of n to the input x of n. So first of all, for that, here's our solution for that, for the difference equation of the system. So here is the statement that we've got here for the question. h of z is just y of z over x of z. So y of z is our output z transform, x of z is our input z transform. So we can just rearrange this as y of z is multiplied by 1 minus 0.64 z to the minus 2 is x of z, and just take the inverse z transform of that. So everywhere we've got y of z, and then it's y of n. Every time we've got y of z, z to the minus 2, it's y of n minus 2. So this is y of n minus 0.64 n minus 2 is an x of z just transformed into x of n. So once you get the hang of these, you can just do them by inspection, pretty much, to go immediately from the z transform to the inverse z transform here. And normally, we'd rearrange this so that y of n is a function of something. So we'd always put y of n scaled by 1 on this side. So it's x of n, and then we've added 0.64 y of n minus 2 to both sides to cancel that one out to give us plus 0.64 y of n minus 2. So actually, although this may not have taken very long, in this particular case, this question gave 25 marks for that. So it's really quite a lot of marks for perhaps a straightforward answer. Did I miss something? No? Okay. Okay, so we've got the solution for there to this. It's sure enough, this is a causal system in terms of it's dependent on x of n and y of n minus 2 only. So it's dependent on the current and past values for things. So that's just something that we can check. So the next part of the question, plot the discrete impulse response of the system. So we want to now work out what would happen if we gave an input which was an impulse response into that system. In other words, here's our system. What if x of n was just a delta of n? So again, looking at the solution for this one, we know it's causal. If the focus will just hold in for a moment. We know it's we know it's causal, so we know that the response h of n is 0 for n less than 0. So that's one of the things that the causal nature is telling us. So anything less than 0 is going to be 0. And in particular, that helps us because we need to know what y of n is for values less than 0. And that will tell us that. So now we've got our impulse response, which we originally had y of n is x of n plus 0.64 y of n minus 2. But now, because if our x of n is delta of n, our impulse is an input, that means whatever comes out of the system must be the impulse response. So we've actually just written this as h of n. If you prefer, you could write y of n here instead. But we've got h of n is delta of n plus 0.64 h of n minus 2. No, maybe, yeah, somebody turn off whatever alarm, please. But because we know it's causal, we know that if n is equal to 0, for example, then n minus 2 is equal to minus 2. Everything finished? Yeah? Right, so now we can start to run this through by saying we know that the impulse response is 0 for anything less than 0, so let's start at 0 and crank the handle forward. So h of 0 is delta of 0 plus 0.64 h of minus 2. We know that h of minus 2 must be 0 because it's a causal system, so all the negative values of h have got to be 0. But delta of 0 is equal to 1, so that means we can immediately calculate our output as 1 at n equals 0. Let's now run it forward. So h of 1 is delta of 1, but delta of 1 is 0. Delta of anything is 0 except delta of 0. And 0.64 h of minus 1, this is also 0 because it's a causal system, and causal systems have a 0 response for any negative n. So this is also 0.
Oh yeah, you did say
So then we go forward to h of 2, that's delta of 2 plus 0.64 h of 0 this time because it's n minus 2. So delta of 2, all of these are all 0. Delta 1, delta 2, delta 3, they're all 0. But what we've picked up here is we've picked up the output 2 steps earlier and multiplied it by 0.64. So this was 1 from here, multiplied by 64, so the output is 0.64, so that's 0.8 squared in this case. And we can just run this forward, or pretty much from there, it's clearly going to be 0.8 to the n if n is even, or 0 if n is odd. So this is going to be what our output looks like. It's going to be 1 followed by 0.64 followed by 0.64 squared, but only at the even value points. So that's our impulse response. So that took us a little bit more of working out, but it actually wasn't really hard. It was just a matter of plugging the values into our impulse response system and realizing that the impulse response is what you get out if you put an impulse into the system. Any questions on that bit? Okay. So let's look at now the next part C. Plot the pole zero diagram for our system. So this is now something that we're going to be going back to the Z transform to do, our pole zero diagram. So this is now our x of z. So we were given this. Let's just turn this over to avoid confusion here. So we're given this 1 over 1 minus 0.64 z to minus 2. But to find the poles and zeros in the z plane, we need this in terms of z, not z to the minus 1. So how are we going to get this in terms of z instead of with a z to the minus 2 in the bottom? Any suggestions? Yeah, multiply top and bottom by z squared. So then that gives us z squared over z squared minus 0.64. And we want to find the values that make the top value 0 and the bottom value 0. And so actually we need to find the roots of z squared minus 0.64. Now in this case, you might look forward here, but what would you call this if you can factorize z squared minus 0.8 squared? Difference of 2 squares, yeah. So if you can spot it's a difference of 2 squares, then you can do that straight away as z plus 0.8, z minus 0.8, multiplied together at the bottom. And we've got z squared. If you didn't spot that, you could use a general quadratic equation solver to find that, but you get the same solution. So then here's the, sorry, that's a little bit out of focus there. So here's our solution. We've got poles at plus 0.8 and minus 0.8 because z plus 0.8 is equal to 0 gives us a pole at z equals minus 0.8, and z minus 0.8 equals 0 gives us a pole at plus 0.8, and we've got 2 zeros and 0. So for the full marks for that, do make sure you get both zeros or both poles if you've got a repeated one, like a squared version or something. So the next part of the question from there asks us to sketch the magnitude frequency response of this system. So without doing any calculations first, what can we say about roughly where the higher parts and the lower parts of the magnitude response are going to be, just based on the pole zero diagram geometry? Where are we going to get the highest responses? Near the poles. So the poles, think of the poles as things that push up the response up towards infinity, and the zeros are things that squash down the response down to zero. So our frequency response are round on the unit circle. So when we've got the unit circle close to one of the poles here and close to the one of the poles here, it's going to be a higher response. When it's as far away from the poles as possible at these sides, it's going to be a low response. And this is our zero frequency here, with the maximum around this side and the negative maximum around that side. So what this says is that at the low pass filter, at the low pass end, we're going to have a high response. At the high frequency end, we're going to have a high response. And in between, we're going to get a sort of lowish response. So even if you didn't have time to do the calculations, you could still do a reasonable sketch to get some of your marks just by knowing that you're going to get a higher response here and here and a lower response in between. But to get the full marks for this one, we'd want to do some calculations of what responses we would actually get. So we want to know our frequencies, h of j omega, magnitude frequency responses, which is when z is on the unit circle, so z is equal to j omega on the unit circle. And some easy values for us to calculate. We can calculate omega equals 0, omega equals pi, and omega equals pi by 2. And let's just bring this diagram back down again so you can see. So omega equals 0 is here, omega equals pi is over here, and omega equals pi by 2 is round at this side. And because everything's nice and symmetrical in the I minus I axis, then the response up here is going to be the same as the response down here for a real valued system. So sure enough, at omega equals 0, that's z equals 1. We just plug z equals 1 into our h of z formula, which is 1 over 1 minus 0.64, which gives us 1 over 0.36. So that's about 3. At omega equals pi, we're actually at a symmetrical point over here. We're the same distance from a couple of poles, so we actually get the same value. And then finally, at omega equals pi by 2, we're around here at z equals I. Well, we had our z was 1 over 1 minus 0.64 z squared. Take our I squared is minus 1, so it's 1 over 1 plus 0.64. So about 1 over 1.64, about 0.6. So then we can plot our curve here, and that's the curve with all the values. So we're about roughly 3, roughly 0.6 down here, and this is the low and high frequency ends, which are the same, and the lowest response in there. So we're getting 4 to 5 times the response in terms of magnitude response. So then the last parts of the question for this one state the following: is the system, let's bring just those last bits up. I'll fold that so we can still keep that for the moment. I'll come back to that later. Is the system stable? Is it a bandpass filter? And does the magnitude response reach a minimum at pi by 2? So first of all, for stability, what do we need for stability of this system? It's a causal system, and we know if it's stable. Yeah, and sure enough, if we look at the pole zero diagram, all the poles are inside the unit system circle, so yes, it's stable. The next question was that it's a band pass filter. Is that a band pass filter? Who thinks it's a band pass filter? Who thinks it's not a band pass filter? Okay, so it's not a band pass filter because you'd have to have a low response at the low and high frequency with a band, a higher band in between. So it's actually a band, roughly a band stop filter in this case. And the last part, does it reach a minimum at pi by 2? Well, yes, it does in this particular case. So that's then the end of that question. So really, in this case, the magnitude frequency response, there wasn't a particularly super challenging part of this question, but the magnitude frequency response was probably the fiddliest part for that. Okay, any more questions about that question? So let's go on to question 4. I'll start this one, but then I'll finish that after the break, and I'll speed up for some of the other questions because you've got the hang of how the questions are laid out by now. So question 4, explain the concept of frequency smearing in discrete Fourier transform. What can be used to reduce its effect? So we saw some of that in the lab when we were looking at lab 3 about you do frequency analysis and it sort of causes extra side lobes and so on. Suppose we wish to find a discrete Fourier transform of a waveform with n samples. If n is even, show that this discrete Fourier transform can be calculated using 2 DFTs, each of size n over 2. Why might this be useful? Okay, so where did we do this in the lectures? Anyone remember? Yeah, we did this when we were doing about the FFT. So this is actually a question about the decimation in time process for this. And if we look at the solutions for this one, then this is actually going through the decimation in time process, which is actually also in one of the tutorials. I think you could do the decimation in frequency part for that. So really that's a sort of, it's partly problem solving, but also partly book work thing. This is a common part of the question that might come up. Then the last part for part C, draw a signal flow diagram for that one, and so that's partly showing that we've split our 4-point DFT up into 2 2-point DFTs with the connections between them. So one point to note here, this is not a complete FFT diagram. So I think one of the things I'd say about this type of question, do read the question and answer what the question is asking if you can, rather than what the diagram that you might have remembered from the lectures. Because from when this one was done, some people would write a whole FFT diagram down, which takes a bit more time than this one, rather than actually what's being asked for. But here we're showing the twiddle factors as multipliers on here, as well as the boxes connecting from that side. So that's really what that part of the question we're looking for on that one. So then the last couple of parts on here, suppose we have 2 n-point sequences with discrete Fourier transforms, so x and y have discrete Fourier transforms, big X of k and big Y of k, show that the inverse discrete Fourier transform of this product is a circular convolution in the time domain. So we used this when we talked about circular and block convolutions, and where the result is used to form fast convolution. This is how, by transforming into the FFT domain and doing a multiply, then that's faster than doing the convolution in the time domain. So that's really the part of that question. There, the solutions are in this in the solutions for this question. But again, check the amount of time that you've got to do the different parts of that, because this part gives you a little bit more marks that you've got to work through the calculations for that one, so you can see where that goes. Okay, so I'll take a break at that point. We're just running slightly late, so I'll start again at 2 minutes past 5 with the other questions from there. And also, if any of you gave me your Lab 4 sheets to mark, I will have got you the marks back by email, but I've got them here that you can collect if you want to after that. Okay, I'll see you after the break at 2 minutes past 5. See you later.
You're so
Dad, I haven't heard what you thought about me. Like this. Dad's already upset. It's like, yeah, that doesn't count. Me and Gracie got, I'm not going to be ridiculous.
You just said you were so yeah, but I say if you claim you're modest, you're not modest. That's the thing. Yeah. If you claim you're modest, then I can't go like, guys, I'm so modest.
You're not modest.
Like, I am like modest.
You're not modest.
What? What have I ever said on the best from here? Like I say, now the best from here. I didn't.
I got 98%.
No, I keep saying I got 9. You keep saying no, you got 89.
Just tell me you see with me after I went, what did you get? 89.
I said 9. To be fair, he will sit right next to me.
What did I get? He's copying me out.
Yeah, but now I understand. Don't be fooled.
I said copying the answers. If you didn't understand.
I get that when I put my hood up. I start singing and I'm walking along with the song.
It was when we knew that we were going to this but it wasn't on the glasses.
I didn't recognise you.
I saw your hair, and I was singing.
My hair's in the front. I've never seen my hair in the front.
You can see your nose.
Yeah, I
Is
remember
that?
seeing that.
And I didn't say, who's that? I was like, no, it's two of them. Who's that? I said, no, that's one of them.
That's one of them. You got your head
I
right.
was like,
Because you were wearing the hood and you had the hair up, so how was I supposed to see the hairline with the hood and the hair on? And from a distance I
you're
can't.
just supposed to know our faces by now.
I know, yeah, but not by that. Sometimes you see a bit different and then you're together. Like when you're together you're different, when you're separate, you're still a bit different. Me too.
Who just said better? Go on.
It's better.
Yeah. Go on,
I
we're
am.
going to go around. Sit around.
All of you three.
It's going to be Gracie. Mine's Gracie in this one.
No, I'm gonna say.
Me, Gracie won't let you. That's such a cop out.
Well, what is it?
How are we going to get a lender?
I don't have a favorite.
I don't know. It's just like,
You just like
I don't
yeah.
I don't like either. I don't like it.
I know. I feel like I'm smiling way too much. Yeah, but your face is not sore. That just made me happy.
Use it. Come on. Copy the answers. Okay, let's actually do it.
I should probably finish this in like 2 hours.
Yeah, we're gonna do it on our own. I do, but they don't.
So what's the details?
Hang on. But we also have the is this for your specific job? What are you doing? Whoa. It's good. I should know what you're doing. Really well.
Is that Jay Butler? Jay Butler.
Why? Can we explain this?
Did you do 6 weeks?
Everything. What was that? What is that?
So you started original.
Which is the entire allowance? What date is it? Whoa! This is here. The trade percentage is 1,000%.